Hello, everyone. Today I'm going to talk about the probabilistic expanding universe and the functor of function theories. This is a talk which was also presented as a poster in 50 years of Hordensky, Gravity, exploring modification of gravity in July 2024. Here on the right part, you can see a functor of function theory interpretation where a car trying to pass through a room and it has some path that is allowed and some path that is not. And here this shows the changes in the actionic fluctuation. And here you can see a space-time which is flat, a 2D one, then a red one which is a 2D curve, and then an orange one which appears and disappears, and it also has some curvature, which is part of the probabilistic manifold spacetime. My short outline is the following. I'm going to introduce the ideas of modifications of gravity. Then I'm going to talk about functor function theories, which are extension of modifications of gravity theories. Then I'm going to talk about a probabilistic spacetime, which then it is interpreted in a probabilistic expanding universe. And then I will conclude and give some outline. Let's start with the introduction. You see, in a cosmological gravitology framework, what we can see here is that the general relativity is a unique theory of massless gravity. And this can be well described by the action, which is the integral of the infinitesimal volume of or your actual volume of the square root of the negative determinant of your metric, and the Lagrangian here. Now, how we can extend this model? We can either break some assumptions, add some field, or add some massive gravity. We're not going to focus on this, but we're going to focus on this too. Now, in additional field, we can have an addition of a scalar field, a vector field, or a tensor field. The most popular ones are the scalar ones, which are generalized by Hordensky. And this Hordensky theory basically comes from the known Hordensky, who generalized a set of other type of theories that are scalar theories. Now, there were also some theories beyond Hordensky, which extend those models. Now, breaking assumption means that we can break isotropy and homogeneity, consider non-homogeneous, non-isotropic universes, break locality, non-local universes, or causality, non-causal universes. Now, another breaking assumption is that instead of considering 4 dimensions, 3 of space and 1 on time, we can consider extra dimensions. And beyond that is the probabilistic dimensions. Beyond that, there are also non-Riemannian geometries, such as curvature types of f of r to the power of n, torsion types f of t, non-metricity fq, and combined frtq geometries, which result to frtq cosmologies and gravities. Now, an extension of that, of all of these theories, is the functor of functions theories. And why is that? You see that breaking assumption means that this will change this part of the integral. By adding some field, like a scalar one, we might have an addition of the following. Small technical error, but we can continue here. So breaking assumption means that we are going to break this part of the integral. If we add the field, we're going to modify the Lagrangian or any other tensor or vector field or a massive gravity. We still modify this part. So a natural way to expand all those theories is to build some theories where the action is just an element. And therefore, we can build functionals of the action that can produce other theories. And let's see what follows. So in this talk, I'm going to talk about the functor of functions and the probabilistic dimensions. Now, functor of functions. Functor of functions. Here is an action. What is a functor? Functor is the generalization concept of a functional, and functional is the generalization concept of a function. Therefore, here's the idea what a functor is. Generalize the concept, and you can connect different objects, mathematical objects, together in a more abstract way. Now, action in physics is a quantity which is the product of energy with time. An action is a quantity which tells us the amount of possible ways a particle can travel from one point to another within a certain region. Therefore, when we combine functor and action ideas, we create the functor of function theories, which predict the existence of axionic fluctuation of field particles, which is an analog of the energetic topological fluctuation of field particles in nature. Now, instead of an action, I can have an integral of the possible actions of some kernel of an action as well. And this will build some new type of theories, effective field theories of actions. And therefore, there's a huge set of functor functions theories out there that we can explore. You can find the details in the paper. Now, there are some limits we can get from these theories, which are GR for density inflation effective field theory of large-scale structure and strings. As an example, here is GR. In the set of functor function, there's the element of an integral of possible actions. Now, this integral can be simplified to an integral between 0 and s. And in the GR limit, this s here can be the GR action, which results to the common action of R, which is the Ricci scalar, and Sm, the matter action. And here are the details of this action. Another limit is the string limits, where we can show that the functor function is also reduced to the string theory by just assuming that this S here is the string action. And therefore, all this integral here can be put here, which is part of the integral functional or function. Now, here are the details if you want to skim through. Now, there are some concrete predictions of modification of Einstein field equation from the functor of functions theories. And here is the simplest one. The simple functor of function action can be modeled as the standard Ricci action, the curvature action, modulated by a beta parameter, plus the standard matter one, plus some exotic S3 action, which is a fluctuation of the standard gravity action. And how this will proceed? We take the action principle and we're going to minimize it. And you see here, we end up with these equations. And this equation results to the Einstein-Friedman equation, where here is the beta, which is the same beta as here, parameter, the stress energy tensor, and here is the fluctuation of a Lagrangian. This fluctuation of Lagrangian is related to the fluctuation of the action. Therefore, we have prediction of axionic fields similar to the energy fields that we have been using so far. Now, let's see how we can constrain this prediction of modification of Einstein field equation through functor of functions. The predictions can be done by choosing a special Lagrangian fluctuation. This fluctuation of the tensor can be modeled as just a fluctuation of the Lagrangian, which is a number, times a tensor here, a 2D matrix, which has only one component, the energy density here. Plug that into the equations, and you end up with a new stress energy tensor that looks like that. And this stress energy tensor now, we can compute further, and we can find that the equation of state looks like that, minus parentheses 1 plus the fluctuation of the Lagrangian to the power of minus 1. So if we constrain the equation of state with minus 1.1, we end up constraining the Lagrangian fluctuation minus 0.1. And what does this tell us? That the axionic fluctuation is 1/10 of the observed volume. If you have d dimensions, you have an observed d volume. If you have 3 dimensions, you have a 3 volume. If you have 3 plus 1, you have a 3 plus 1 volume. And that's 1/10 when we constrain the equation of state to be like that. Now, under this reasonable assumption, simple actionions are 1/10 of the observed volume. Now, the constraints and prediction of modification of effective field theory are the following. We can assume a quadratic effective field theory. In that case, we have the standard Ricci curvature action, the standard matter action, and we modulate it by beta times a quadratic term that has as a base the S of R. Therefore, by the stationary action principle, we can work out the math and we can find this modification of Einstein field equation, where you can see here the Einstein tensor, which are second order derivatives of the metric, the stress energy tensor, which are constants as a function of time, possibly, but there are no derivatives here. And here you can see an integral of the Ricci scalar, which are basically integrals of your metric. Therefore, these are integral differential equations of your metric that This is the first time integral differential equation was applied in gravity and cosmology. Therefore, we have to solve this type of equations, and you can think of this integral as a modification of the gravitational Newton constant. We can have an effective gravitational Newton constant, that is the gravitational Newton constant, plus some modulation here that is controlled by beta and this type of integral. Now, what we're doing now, we're working solutions through the dynamical analysis system to solve this type of equations. Now, an example of actionic field interpretation is the following. Action answers to the question, what is the number of all possible routes a cat can use to pass through each room? So here is a room, entrance and exit. Then a cat can take this path, it can jump, it can do other stuff, it can take multiple paths. But let's assume that it can take just 2 paths within this room. Now, in a room further apart, the same size cat, same size room, but now we have a blockage in between. Then this path can be taken, but this one no longer. Therefore, you can see that x1 is possible for both rooms, but x2 is not possible for the second room. So you see here I have only one path allowed. If I had n, here I will have n minus n, and red is the number of paths that are blocked by the block. Therefore, the amount of number of paths is different for each room, so the axionic field is different for each room. Therefore, in between there's some space, therefore there's an axionic field everywhere. And using a quantum mechanics argument, if there's an axionic field everywhere, then there's an axionion field particle everywhere. Hence the prediction of axionion. Now let's talk about the second part of the talk, which is the probabilistic universe. Now, we talked about to extend general relativity, we can break some assumption, add some field or massive gravity. In the breaking assumptions, we can think about probabilistic dimensions. And this paper is under review currently, and you can find it online if you have any comments or questions. Now, the first motivation about these studies is the following, that in 42, Menger have introduced the concept of statistical metrics. And in 77, Drossos introduced the stochastic Menger spaces, hence the probabilistic spaces. In the framework of modification of gravity, we have a huge history of string theory which predict extra dimensions, while on the opposite side, there are many physicists which work on loop quantum gravity theories which predict the non-existence of metric. So you see here, we talk about metrics with extra dimension and space-times without metrics. So what is in between? So it's natural to introduce an idea in between, which is the idea of a probabilistic manifold, which is between extra-dimensional space-time manifold and non-metric manifold. Here it should say probabilistic. Now, the second motivation is that we have some evidence for a semi-analytical model which have found that the dimensions are 4 plus or minus 0.1 from gravitational wave estimates. This was a study done by Pardo, Fischbach, Holz in 2018. And basically, it tells us that there is no precise estimate of the dimension. Therefore, we can still look for probabilistic dimension, even though this is an estimate of theoretically one number of dimensions, we can have a probabilistic number of dimensions. Therefore, we talk about probabilistic dimensions. Here is a 2D space-time continuum. It's easy to generalize in 3+1 if we have in-person discussion at least. Now, a 2D curved probabilistic space-time would look like that. You see that according to some parameter, we can think of this parameter at the time, the space-time appears and disappears. Therefore, this introduces the concept of probabilistic space-time. Now, we can also have a 2D spatial probabilistic that expands. Therefore, we have the 2D spatial curve probabilistic and expanding metric. Now, probabilistic dimension turn up probabilistic gravity. So instead of having D dimensions, 4, for example, we can have the 4, but this 4 might come from a Gaussian, which has a mean 4 and a standard deviation. Therefore, if we think of extra dimensions, we can have D here, dimension, and some extra d standard deviation on this Gaussian. Now, modifying dimension means that we need to modify topology, metric, manifold, curvature, etc. But also means that the matter content, the energy content, is going to evolve differently than before, because it's going to evolve in a topology which has probabilistic dimensions. And here you see how this is going to be constructed in the action. At the action level, the probabilistic gravity will model by an integral of a probabilistic infinitesimal element, a determinant which includes the probabilistic spacetime, the Ricci scalar in a probabilistic spacetime, and the matter content is going to be evolved in a metric and a spacetime that is probabilistic. So there are sophisticated and simple modifications of gravity to consider probabilistic dimensions and turn up probabilistic gravity. So now, for the moment, we're going to consider simple modifications. Simple probabilistic metric would look like that, which is the conformal per tube FLRW metric. And here we have scaled the time component by a P function, which encapsulates the probabilistic nature of spacetime. You can see details in the doc, as we have said. Now, what are the results assuming such metric? The Einstein field equation results to modify Friedmann equation, which looks like that in conformal time. Here is the Hubble expansion rate, here is the scale factor A, and here's the probabilistic factor. Here are the standard energy density ratio components, and this is the equation of state for its energy density component, which are the first and second Friedmann equation that describe the background evolution of the energy densities. While continuity equation remains the same, there is no effect from the probability function of the spacetime. Currently, we're working on a solution of this type of equations. Now, the probabilistic per-tube expanding manifold metric modifies the Einstein-Boltzmann equation that describe the perturbations. And therefore, you can find also those in this doc according to the previous assumption statement. Now, some other qualitative results are the following. Connections of probabilities with information. We know that the information of an event is equal to the negative logarithm of the probability of an event. So a new kind of manifold metric pairs using probabilities and information can be considered. Now, a step further is to correspond these field particles and characterize new types of particles that are more fundamental than the ones that we know so far. And we can consider them depending on the space that they take up. So we have energetic field particles because they have some energy. So these are energies. An electron has mass, charge, is localized in space, has some probability, and is localized in time. Therefore, what is more fundamental than calling all these properties as an electron? It's the properties that can be also particles that create this complex particle. And we can have a spatialium, which is basically the spatial space localization of the particle. We can have a tinion, which is the temporal localization of the particle. We can have the probablon, which is the probabilistic localization of the particle. And in a sense, if you consider all these three informations, plus the mass or energy or action, plus the charge, we can talk about informatons because these are informations. Therefore, we might reconsider the way we describe the particles by considering more fundamental particles that has this type of structure. This is a bit philosophical, and we leave a future formulation of this in a future work. Now, let's have some conclusion. So the conclusion are the following. We have mathematical and observational evidence for functor of function theories and predictions of the actionions. And we also have mathematical and observational evidence for probabilistic dimension, probabilistic manifold metric pairs. And what to also predict, we have prediction of spations such as spatialions, tanions, probablons, and informators. So what are the future axes of research? To develop 5 axes of research according to functor of functions cosmologies, probabilistic and informatic cosmologies, non-Riemannian cosmologies, dynamical analysis systems, numerical and analytical solutions to the above theories, and produce some statistical tests of above theories in the early, late universe, and gravitational waves. Of course, all that can happen with the collaboration on those models and tests with other cosmologies. So I would like to thank you for your attention. I will leave you here the reference. You can pause the video and search for them, and talk to you soon. Thank you for your attention, and bye-bye.